All right, 17. 17, this introduced us to entropy and Gibbs free energy. All right. This equation, the ideas of it show up constantly on our tests, right? There's a lot of this going on there. All right, what does delta G tell us? Spontaneity, all right? A negative, if delta G is negative, that means that we're spontaneous or thermodynamically favorable. Negative, positive value, non-spontaneous or spontaneous in the reverse direction. All right. What does delta H tell us? If delta H is negative, we got exo, positive, endo. Delta S, what's that? That's our entropy. If that's a positive value, what does that tell us? More disorder. This is the one where we could look at an equation, a reaction, and get an idea about what our delta S is going to be. Less disorder, more order. Right. So we could look at an equation and have an idea whether the delta S is positive or negative, and whether it's going to be big or small. Okay. Focus on gases on that one.
It goes towards the side of less, or if it says like the delta S decrease, we can say it went in like the direction of fewer moles.
So we're not at equilibrium, so we're just like a reaction. We're going to see if a reaction occurs or not. So we might have like we might have this. From that, we can get an idea about what the delta S is going to be. Here, we're going from 3 moles of gas down to 2 moles of gas. That means we're becoming more ordered. So our delta S is going to be a negative value there.
Are all equations like one way spontaneous, the other way non-spontaneous?
Yeah, unless there's a temperature where you're like your delta H could equal your delta S. So like that term, so it could be 0, so you could be at equilibrium. But yeah. All right. So we have those ideas right there. Could we tell just by looking at an equation if it's endothermic or exothermic? We're not great at that. There is one example, though, that we know it's exothermic. What's that? Combustion reactions, right? A combustion reaction, a fuel plus oxygen yields carbon dioxide and water vapor. That's going to be exothermic. All right, so now we can put these together and predict whether an overall equation is going to be spontaneous or not. When these are opposite signs, when our delta H is negative and our delta S is positive, those are reactions that the universe likes. They like exothermic. Exothermic reactions give up energy that's stored in bonds. Right? The universe likes getting rid of that energy that's stored in bonds, so it's in a lower energy state. The universe likes disorder, likes everything in disorder. So when we have these, no matter what, our delta G is going to be a negative and it's going to be a spontaneous reaction. Right? And if we have the opposite, where delta H is positive endothermic, our delta S is negative, it's becoming more ordered, our delta G is always going to be a positive value, always going to be non-spontaneous or spontaneous in the reverse direction. All right, when they are the same sign, that's when we got to think about what factor matters then when they're the same sign. The temperature, right? Because if delta H is negative, but it's becoming more ordered, this term is going to be negative, this one is positive. So at low temps, my delta G is going to be based on the delta H term, right? Low temperatures, this gets smaller and smaller. My delta H will be negative. At high temperatures, there's eventually going to be a temperature where this minus T delta S is going to be greater than delta H, and that's going to turn non-spontaneous. Spontaneous in the reverse direction.
Is temperature and in Celsius or Kelvin?
In here, Kelvin. Anytime you ever have to like just multiply something by temperature, the times that we use Celsius is we do change in. When you do change in temperature, delta T, that it could be Celsius or Kelvin, because 1 Kelvin is 1 degree Celsius.
Okay.
And then we have the opposite, endothermic, but becoming more ordered, right? So now at low temperatures, my delta H is positive, but at high temperatures, then my minus T delta S term is going to become more important, and it's going to be spontaneous. Good? Good. All right. Last chapter that we did. We got our electrochemistry. All right. We got our cells. Looks something like this. All right. I almost didn't do this picture, though. Why? Why did I almost not use this diagram? Capital L, like what? Amateur hour. All right. This is the standard how they show what the cell is. This is telling me there's a zinc solid in a solution of zinc sulfate. That double, that's like the break, and then the other cell, the other electrode, I have aqueous copper and solid copper in there. All right. So this is our standard here. All right. At the anode, what process occurs? Oxidation. How do we remember that? Vowels. Cathode, reduction occurs. Remember that because of the consonants. In general, we say the cathode is positive and the anode is negative. Okay. Since the oxidation is loss of electrons, that means our electrons are leaving the anode towards the positively charged cathode. If the salt bridge wasn't here, what would happen? It would really stop, because what would end up happening is this side becomes negative because the electrons pass there. So more electrons wouldn't want to flow towards that negative. This side would get positive, so we wouldn't want to lose electrons. Because we can picture this here, my zinc ion, or my zinc metal, is losing electrons and turning into zinc ions, right? And my copper ions are precipitating out on there, using those 2 electrons to form copper atoms. Salt bridge is there to balance that out. Here, since we're losing the electrons, the Cl's would be drawn this way. Here, since the electrons are flowing this way, those K pluses would go to try to balance out those charges. All right. We've been given equations, standard reduction potential. So if we're thinking about this particular equation here, right? Standard reduction potential would look something like this. We would have Cu2 plus 2 electrons yields Cu. This is what they would give us these equations. It's standard reduction potential, meaning both of these equations show reduction occurring, right? We're adding electrons to our ions to produce those solids. All right, I have 2 values. What's that, negative 0.76? Zinc, let's see. Oh, I got it. All right. Zinc, negative 0.76. Cu, 0.34. All right. How do I know which one's the anode, which one's the cathode? Right, because my E of the cell is going to be E of the cathode minus E of the anode. The cathode is the larger one. All right. So if this is cathode, right, this shows reduction. So what do I have to do with this equation when I go to write a balanced equation? This is going to get oxidized. Is this showing oxidation? So what do I have to do? I have to flip that equation around, and now I can add those up and get the overall equation for them, right? My 2 electrons would cancel out. If I didn't have equal amount of electrons, I'd have to multiply one equation to get those numbers to be a common number of electrons. And then I can do cathode minus anode, and I'll get my cell voltage.
The cathode is the bigger number, right?
Cathode is the bigger one, yeah, where reduction is going to occur. All right. Delta G, K, and E. Delta G, we said spontaneity, right? What does E measure? The cell potential of our electrochemical cell. K, that's our equilibrium constant, right? When delta G did I have that one? Delta G is negative. That means E is going to be a positive value. We're always going to get a positive value for that. We got an equation. Minus NFE. So if E of the cell is positive, that automatically makes delta G negative. And here, K is going to be a really big number. If the reaction is spontaneous, that means I'm going to get a lot of reactants turning into products. I'm going to end up with mostly products at the end. If delta G is a positive value, that would mean my E of the cell is negative, and my K value is going to be really low. How can I get a negative E of the cell? What do I have to do? I have to put something up there. Instead of a voltmeter, I'm going to put a battery. I'm going to put some kind of power source to force electrons in the reverse direction. This is the whole idea of us recharging our cell phone batteries, recharging anything. Because as the process occurs, we're going to start ending up with not enough reactants on this side, too many products. So we got to run it in reverse to recharge that battery back up. And that's where we can have an electrolytic cell. Means, right, we got to add electricity to get that reaction to occur instead of it spontaneously giving us energy. Questions on the batteries? First off, concentration effects. So here, this is assuming I have 1 molar, 1 molar. Right. All right, if I had this, if I was able to increase the concentration of my Cu2 plus ions, instead of 1 molar, let's say I did 2 molar, what's going to happen to my cell voltage? Normally it's 1 molar, so my reaction's occurring. I double it. Now, think of Chatelier's principle. I've increased my reactants, so I'm going to get more of the forward reaction. Right? I'm not at equilibrium. It's not stopped that I'm forcing it one way or the other. I'm just either speeding up or slowing down the reaction. By adding extra reactants, I'm going to speed up that reaction. So my cell voltage is going to increase. If I did the same thing to my zinc, Now I've increased this. Now my product side is too heavy. It's going to slow down the forward reaction, and I'm going to end up decreasing my overall cell voltage. Right. That's the effect of concentration on those values there. Batteries, again, special closed system. It's this in a more usable form. A fuel cell, similar, like we had one of those on our practice problems, was a fuel cell. Again, we could just treat it as an electrochemical cell, looking at our equation, knowing that it's still going to be cathode minus anode. We're still going to flip around that anode equation, leaving that cathode one alone. Corrosion, just spontaneous reaction, right? We try to prevent that corrosion. And then we have our electrolytic cell that we said with a negative cell potential. All right, questions? George, how confident are you right now? George, go ahead.
I thought I think that's I'd say 5 out of 10. Like, I'm not confident. But for the concentration effects, do you have to calculate the voltage of the cell with that? Like, if there's two more, or do you just have to know what increases and decreases?
There is an equation for it. I don't believe we're going to have to use it.
Okay.
We would have to do it qualitatively, then quantitatively. Questions?